Welcome back to your Chem 3 lecture. We are going to finish out Chapter 9 today on basically the electronic structure of atoms by talking about the quantum mechanical model that supersedes the Bohr model that we were talking about in the previous chapter. So as we saw in the last slide of the previous lecture, the Bohr model was really good at predicting the transitions that we saw for hydrogen, but hydrogen atom is a very simple system with just a single electron. So while it was good at that, it turned out that if you introduce another electron into the system, for example, with helium that has two electrons in a neutral helium atom, the Bohr model couldn't handle it. So there must have been something else going on. So now the reason that we introduced the Bohr model first is that it's a pretty good way for us to wrap our minds around it, whereas the quantum mechanical model, which I'm going to teach you about now, is a little more complicated and kind of harder to understand. The main difference is going to be that we're going to replace the orbits that we saw, those circular lines, the way we were thinking about it, like planets circling the sun, with what we call quantum mechanical orbitals. So no longer orbits, they're now orbitals. And they look a lot different, unfortunately. But we'll get there when we get there. Now, the way that orbitals are primarily different is that rather than showing like the distance to the nucleus, they just show a statistical distribution of where an electron is likely to be found at a particular energy. So the orbit represented its energies with the distance from the nucleus. Now orbitals are just going to give us kind of a probability map that shows around where those electrons are likely to be found. Ooh, hold on. There we go. Okay. Now here's the deal. The reason, and you're not going to be expected to know all of quantum mechanics or all of particle physics in this Chem 3 class. But we do have to introduce it to you because it's critical to understand the behavior of electrons. Number one, electrons are basically responsible for almost all the chemistry that we actually do and we see. Most of what we see as far as chemical reactions, we're watching electrons go from one place to another. And so we need to understand the behavior of electrons. And the thing is, electrons are so small, they have such a small mass that they exhibit a very strong wave-particle duality. In other words, in some cases, they behave like a particle, and in some cases, they behave like waves. So because they don't exactly take the shape of particles, because they have this wave function aspect, we can't give like an exact path for where they go from and where they go to. It's not like a baseball is the way you can think about it. Instead, it's like a baseball that can turn into a wave and then show up in a random spot. So again, this orbital is going to be a probability map, and it's going to show where an electron is likely to be found when you look at an atom. Okay, so, all right, this is our analogy here is with baseball. So for baseball, if you're watching a baseball game, the pitcher throws the baseball from the mound to the catcher, and that baseball follows a certain path. Now, depending on, how good the pitcher is or what pitch the pitcher is using, that can be, have a few different patterns, right? It could be a curveball, could be a fastball, but always the ball follows some type of linear path where the, it goes from here to here, and you can follow it discreetly at each step of the way. Even on the most complicated pitches, that's just where, things curve, basically. But even the curve describes a line or a path that the baseball follows. Unfortunately, with electrons, you can't describe this kind of path because what we call wave-particle duality and this uncertainty principle. You may have heard of the uncertainty principle when you've heard about Schrodinger's cat before. That's the one that's in the box that might be dead or alive, so it's both at the same time. Well, as it turns out, with particles and waves, so especially like very small particles like an electron, you can either know its location or you can know how fast it's going. So you can know its location or its velocity. But the more you know about one, the less you know about the other. The way you can think about it is like this. So think about how we see a baseball, right? We see a baseball because light reflects from the sun, hits the baseball, and then bounces off of it and comes into our eyes. Now imagine doing that to an electron. Electron is very, very small. And in fact, if it absorbs a light, or if light bounces off of the electron, the speed of that light is going to affect the path of the electron. So we maybe saw where the electron was, but now it's going to be in some place totally different, and we can't predict where that's going to be. Okay, so the way that we keep track of electrons is, rather than focusing on a single electron and trying to like track it, like it's the Earth orbiting the sun or the moon orbiting the Earth, instead what we do is we run hundreds of experiments. So if you just like measure 100 electron flows, then we could see a statistical pattern of where those electrons are likely to be. So this is what we're going to see here, and this is what we call the probability map. This is what our orbitals are going to look like. So this is an example of like a quantum mechanical baseball model. So if the pitcher was pitching electrons instead of baseballs, they might be close to the nucleus with about a 20% likelihood, and then slightly farther out there's a 40% likelihood, and then the farthest out that we see here sketched is a 70% likelihood. Now that leaves a whole 30% of basically the rest of the universe as a place where the electron could be. So that's what we're going to be focusing on today. So again, we just want to focus on, we've got these electrons. We don't know exactly where they are, but we can describe to a certain degree of certainty. Usually we use 95% certainty maps, where it's likely to be. Now, if that sounds complicated, it's because it is. And it's not necessarily something that's like, it's not intuitive, right? We're used to seeing baseballs and knowing how baseballs perform, but electrons just don't behave in the same way. Okay, so let's go ahead and talk about orbitals. Now, the beautiful thing about orbitals is this is going to help us understand the periodic table even better. Okay, so for the quantum mechanical model, a number and a letter are used to specify an orbital or a set of orbitals. The lowest energy orbital in the quantum mechanical model is the 1s orbital. So number 1 and letter S, that's two separate things that you need to keep the track of, okay? So the number 1 and the letter S. The number is what we call the principal quantum number, and that's also known as N. And what this does is this acts like Bohr's energy levels. So that's why we use N. It's kind of the substitute for what Bohr had as his energy levels. So we got N equals 1, N equals 2, N equals 3, 4, 5, all of the counting numbers. And this is what we call the principal shell of the orbital. Okay, now, so if this is the lowest energy orbital, that means that the first electrons that go into any atom are going to go into the 1s orbital. So think of just a unexcited, totally natural state hydrogen atom at room temperature. The first electron that you add in there is going to be going into the 1s orbital, the lowest energy orbital. This is what's known as what we call the ground state. Now, as we saw in the previous lecture and in lab, when you excite electrons, they can go up from the lower energy orbital, from the 1s orbital, to a higher energy orbital, like one of the ones we're going to talk about. In that case, we would say that that is in an excited state. So again, that electron can absorb energy, just like what we saw when we were explaining the Bohr model. But now we know it's not going from like one rung of a ladder to another. Instead, it's going from a 1s orbital to a higher energy orbital. So we're just kind of trying to define all these terms. Ground state, that's the lowest energy state of an atom. And the excited state is where electrons have absorbed energy and they have been promoted to a higher energy orbital. Yeah, so all atoms of each element have a single ground state, the lowest energy state. I mean, it makes sense, it's the lowest energy, there could only be one. And then the number of excited states is virtually infinite, if not practically infinite. Okay, so let's go ahead and start with the numbers. So we're going to talk about the principal quantum number first. Remember, the principal quantum number, that's the N. So for 1s, that's the 1. Now, as I mentioned, these are the counting numbers. So they go 1, 2, 3, 4, 5, 6, 7, 8. We haven't gone beyond 8 yet, but theoretically it's possible to go beyond 8. And the way this works is as the principal quantum number N increases, the energy of that orbital increases. So the 1s is the lowest possible quantum number, and the lowest energy subshell, the s subshell that we'll talk about. So that is the lowest possible energy, and that's what's going to fill first. And that's why we have it on our diagram here. So n equals 1 is the lowest energy, then 2, then 3, then 4. Okay, so next step. Now we have the letters, and we have only 4 letters that we need to worry about. We have the letter that is going to tell us the subshell of the orbital, and that specifies the shape of the subshell. The possible letters are in order. Of course, S, P, D, and F. Yeah, I'm sorry about that. These are really old terms where we didn't understand what we were looking at when we came up with these terms. So we didn't know how it was related. And so that's why it's totally nonsensical. Like these are archaic kind of letters that are left over from like early 20th century crystallography experiments where they diffracted in one pattern, it was called an S. It diffracted in another pattern, it was called a P, a D, and finally an F. So apologies about that. There's no other way around it than to memorize these. And also it's important to memorize the order. S comes before P, comes before D, comes before F. Okay, so but we're going to start with the lowest energy subshell first, which is the S subshell. And fortunately, it is the simplest subshell that there is. It is simply spherical. Okay, so now we're going to show shapes of these orbitals. But again, remember that these shapes are like probability distributions. They're going to show you with a 95% likelihood that the 1s electron should be in this sphere, is the way you can think about it. Okay, the next part here is a dot density map. We'll take a look at a couple of these. I think they're on the next slide, I hope. Here we go. Yeah, so a couple slides from here. The dot density is going to be just the kind of a way of showing the probability of finding an electron. And you'll see that the highest dot density is closest to the nucleus for the 1s orbital, and then it decreases farther away. So again, looking at here. So if you have a dot representation, you see that you see a lot more dots in the middle, close to the nucleus. This is the nucleus of an atom here at the origin of our graphene. And then as we get farther away, we see fewer and fewer dots. Now, if we just do a shape representation, it doesn't really capture everything, but again, we say 95% probability that the electron would be in here. Okay, did I miss something here? Oh yeah, okay, so just showing the geometric shapes. Okay, and we're showing you the 90% probability maps. You can also see the 95% and even 99% probability maps, but the only difference is basically they just get slightly bigger. But let's focus on the 90% probability maps. So if we show you the 1s orbital as a sphere, that encompasses the volume within which the electron is likely to be found 90% of the time. So, okay, so this is our 90% shape representation here. And as we can see, 90% of the dots in the dot representation fall within the sphere that's in our shape representation here. Okay, all right. Now, the number of subshells in a given principal shell is equal to the value of n. Again, that's our principal energy level. So in other words, if you have the lowest quantum number, 1, you only have one subshell, meaning that the only subshell that exists is the 1s subshell. So the first electron is going to go into the 1s subshell. Now, that means there is no 1p, 1d, or 1f. Those simply do not exist. However, when we go up a principal quantum number to n equals 2, now we have 2 subshells. So now we have the s and the p subshells. Go up again to n equals 3. That gives us s, p, and d subshells. And then finally, n equals 4 gives us 4 subshells, s, p, d, and f. Okay. Now, when you go from the 1s orbital to the 2s orbital, the only thing that changes, the shape stays the same. The only thing that changes is the size. So the 1s orbital is a certain spherical shape. The 2s orbital, being higher in energy, just is simply a bigger sphere encompassing a greater volume. Okay, so once we take it to the 2s, the next one up is going to be the 2p. So the energy, the way this is going to go basically is you're going to start here, I should annotate this so you can see it. You start at the 1s sublevel. This is going to be our first one here. Then we go up to 2s. Then we go over to 2p. So we're going to fill the 1s first, then the 2s, then the 2p. Okay, then we go up to the 3s, and then we go to the 3p. Now here's where things get a little bit complicated, and we'll have to talk about it in a little bit. But this gives us our rough filling order for the first few atoms. I think the first 20 atoms are covered here. Okay, all right. So now what does the p orbital look like? Once we get to the 2p orbital, that's n equals 2, and then our subshell is the p sublevel. Well, actually what it turns out is for the 2p sublevel and all p sublevels, they each contain 3 different orbitals. And these orbitals have the same shape, but they're oriented in different ways in 3 dimensions. So you'll be expected to recognize these orbitals as p orbitals. They're kind of dumbbell shaped is what we say. They're basically 2 lobes. I always think of like 2 balloons tied together. You have what's called the px orbital. That's the one that's aligned on the x-axis. You have the py orbital. That's the one that's aligned on the y-axis. And then you have the pz orbital. That's the one that's aligned on the z orbital here. Okay. So, and again, you would have a 3p sublevel as well, which could contain the same 3 orbitals, but each of them, again, just gets bigger in size. Okay. So what do we know? All s sublevels contain a single orbital that's spherical. All p sublevels contain 3 orbitals, each aligned on the x, y, or z axis. And yeah, they have the 3 orbitals there. And again, they just get bigger in size. And they're dumbbell shaped is what I wanted to say. Okay, then next, we get to the d subshell. So what did I want to say? So yeah, so we have the 3s and 3p subshells. The 3s orbital contains just the single spherical orbital that's larger than the 2s orbital. The 3p subshell contains the 3 p orbitals, px, py, and pz, but again, just bigger in size and higher in energy. And then finally, we get to the d subshell. So n equals 3 has s, p, and d. And the d subshell has 5 d orbitals. And they look like this. So finally, we're getting to some more complicated shapes that are describing the arrangement of electrons here. Now, I know this might seem complicated, but it's important for us to understand the shapes of these orbitals, because you can think of these like the electron's homes, okay? Think of this as like where the electron lives. And as I mentioned before, most chemistry can be explained as the transfer of an electron from one species to another. And so in order to understand how an electron gets transferred from one place to another, we need to understand where that electron is coming from and where it's going to. So these orbitals allow us to predict whether reactions will occur or not, and how they happen. Okay, so now you're not required to memorize these, like the DYZ, you don't have to memorize this, but you do need to recognize these 5 shapes as the D sublevels. Now, the first 4 are relatively straightforward. We have the DYZ, which is a 4-lobed orbital that is in the YZ plane, which is analogous to the DXY orbital. That's a 4-lobed orbital that's in the XY plane. And then the DXZ orbital, again, a 4-lobed orbital in the XZ plane. Now note, each of these, the lobes are between the axes. Now, the 4th orbital here looks similar, dx squared minus y squared. It's 4-lobed, but these lobes are actually on the x and y axes. So that's what makes it different from the dxy. And then finally, the real weird one here is the dz squared orbital. So the dz squared orbital kind of looks like it has a donut around the middle of a p orbital. And so that's kind of the way you can think about it. It's a weird 3-dimensional shape. Now, you might ask yourself, why is it this way? Well, it is the result of a particularly complicated bit of mathematics that you won't get to for a while. Maybe when you're in physical chemistry, they will be asking you to do these calculations. Until then, I won't ask you to do that. You just need to recognize the shapes. Okay, so why do we use the quantum mechanical model? Well, all of these models are going to be based on how well they predict or how well they replicate what we actually see in chemistry. So the quantum mechanical model predicts the bright line spectrum of hydrogen just as well as Bohr does, but it also predicts the bright line spectra of other elements, whereas the Bohr model failed when you went above one electron. So the more sophisticated quantum mechanical model kind of took precedence because it could predict more behavior. Again, the Bohr model, we're only using it basically as a logical stepping stone to get to the quantum mechanical model, but it's important for us to kind of explore in that way and make it to the quantum mechanical model, which is pretty complicated. Okay, so now we're finally ready for the first type of thing that we are going to have sample exercises over. So I know this is what you were waiting for. What kind of questions could he ask me? Well, what I'm going to ask you is basically, I'm going to ask you about electron configurations. So an electron configuration diagram is going to show the occupation of orbitals for the electrons in a particular atom. For hydrogen, that's pretty simple. Hydrogen only has one electron, and we already mentioned it's in the 1s orbital. So we would say that the electron configuration for hydrogen is 1s, that's the orbital that it's in, and it has one electron, so 1s, 1. Now it's going to get more complicated from here, obviously, because we have new orbitals, new subshells, new levels. But if we work together, I think we'll be able to figure out the filling pattern for it just well enough. Okay. So the other way that we can represent this is what's called an orbital diagram. And the way that we do that is for an orbital diagram, we just draw a box, okay? And the box represents the orbital. Now for hydrogen, we know that we have a 1s sublevel. And as I mentioned, 1s sublevels have one orbital. So we just have to draw one box above the number 1s. Okay, easy enough, right? Now we have one electron. So what we do is we draw a half arrow, and it's important that it's a half arrow, not a full arrow, pointing up. So again, what this would look like if I were doing it just in by hand here, we draw a box that represents the 1s sublevel, and it's single orbital. And then we're going to draw a half arrow pointing up. Okay, now, yeah, it's really important, again, use a half arrow, not a whole. Now in the future, when we get to larger sublevels, think like the 2p sublevel. The 2p sublevel, how many orbitals does the 2p sublevel have? I'll wait for you. Remember, all p sublevels have 3 orbitals. So that means we need to draw 3 boxes for the 2p sublevel, like that. For any of the s sublevels, it's always going to be 1 box. For any of the p sublevels, it'll be 3 boxes. And for any of the d sublevels, it'll be 5 boxes for the 5 orbitals that we just saw. Okay, now, you may ask yourself, why is it that we had to draw that half arrow pointing up? Well, I guess you could have drawn it pointing down as well. That's totally fine. But here's the big deal, and this is the big reveal that you probably have been waiting for. Orbitals can contain 2 electrons, at most 2 electrons. And in order for an orbital to house 2 electrons, they have to have opposing what we call spin. So if one is spinning up, the other electron has to be spinning down. That leads us to a situation that looks like this in our orbital, where we have the first electron spin up, the second electron spin down. This, if we were drawing this in an electron or in an orbital, that would be a full orbital because it has 2 electrons that are spin paired. This rule is what's known as the Pauli exclusion principle after the physicist Wolfgang Pauli. And again, it says orbitals may hold no more than 2 electrons and they have to have opposing spins. So the way that we show it is one arrow pointing up and the other arrow pointing down. Okay, is that complicated enough? Well, let's go ahead and take a look here. So if we have multi-electron atoms, the subshells within a principal shell don't have the same energy. So the 2s and the 2p sublevels don't have the exact same energy. So different subshells within the same principal energy shell are going to have different energies. That's kind of what we were saying before, where we mentioned that the 2s sublevel gets filled before the 2p sublevel. Okay, and then there's a further complication, which is that the d sublevels tend to be lower in energy than the the foregoing S sublevels. So for example, the 4s subshell is actually lower in energy than the 3d subshell. And this is due to the interaction of electrons once they're actually in a system. Because remember, as we're putting in electrons, these aren't just like tennis balls, for example. These are negatively charged particles. And what is it that happens when you put a negative charge next to another negative charge? They repel each other, right? So if we have a full 3s and 3p subshell, those are occupying space that the 3d subshell would need to occupy as well. So there's a repulsion there. And so it's easier, it's lower in energy for the electrons to expand out into the 4s subshell before they go into the 3d subshell. So this is what it actually looks like. Now, we don't have to memorize it this way, but this gives us the filling order of the sublevels. So the 1s fills first, followed by the 2s, then the 2p, then the 3s, then the 3p. This is the first break that we really have talked about, where now the 4s fills before the 3d, then the 4p fills, then the 5s, then the 4d, okay? And then where would it go from there? Of course, 5p, 6s. Okay, so I'll show you a simpler way to write this. You don't have to memorize this necessarily. I'll show you a simpler way to write this in just a little bit. Okay, so now let's go ahead and write these ground state electron configurations and orbital diagrams. So starting from helium, helium has 2 electrons, okay? And we know the first one goes into the 1s orbital, just like hydrogens. When we put the second one in there, well, that orbital can fit 2 electrons, right? So no problem. We just write it as 1s2, like that. Now for the orbital diagram, we draw a big box for the orbital, and we label it 1s. We have 1 electron pointing spin up, the other electron pointing spin down. Good to go. So that means that the 1s orbital is filled. So what happens next is we have to go to lithium, right? Lithium's a 3 electron atom as a neutral atom. So its electron configuration is going to start from helium's, right, 1s2, but you can't fit a 3rd electron in the 1s sublevel. Now you have to move to the next sublevel, which is the 2s sublevel. So we get 2 electrons in the 1s sublevel, and then 1 electron in the 2s sublevel. The orbital diagram is going to look like this. We have the 1s sublevel, again full, just like with helium. And now we put our 3rd electron into the 2s sublevel. Okay, now, from there, you could do beryllium, for example. That's 4 electrons. Nothing really exciting is going to happen there, because with all that's going to happen is you're just going to fill this one up, right? So you probably already get that anyways. So what's fun is when we get into the right half of the periodic table with the non-metals like carbon, for example. So carbon has an electron configuration where it has, well, first off, how many electrons does it have? Look at your periodic table. It's got 6 electrons, right? It's Z equals 6. So the first 2 go into 1s2, no problem. The second 2 go into the 2s, that's 2s2, no problem. Leaving 2, well, we have the 2p sublevel. The 2p sublevel has 1, 2, 3 possible orbitals. So you know that it could fit up to 6 electrons. Okay, now we only need to put 2 in there, so it's no problem. It's 2p2. So the electron configuration, pretty straightforward. Now the orbital diagram is where things get a little interesting. In the orbital diagram, because we have these 3, here, let's imagine that I didn't write that already, and let's just have it like this. So this is our 2p, and we need to fit 2 electrons in. Now with the 1s sublevels, what we did is we did spin up, then spin down. But as it turns out, that's not the way things actually happen. Because think about it this way, remember, electrons are negatively charged. So if you try to stick them both in the same orbital, they're going to interact with each other and repel each other. So before each of these has a single electron, they're going to just spread out and occupy these same energy level orbitals as much as they can. Sorry, that's a really bad arrow. So rather than going spin down into the first orbital, it goes spin up into the second orbital here. This is what's known as Hund's rule. And again, Hund's rule says when filling orbitals of equal energy, electrons fill singly first with parallel spins. Okay, all right. So now here is our way that we're going to be able to actually predict the order of electrons filling. Now, there's two ways that you can do this. You can either just remember it's 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. And that's enough. We won't really do beyond that probably. Or you can remember this pattern. So if you draw all the s sublevels out like this, so 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then next to it, put your p's, so 2p, 3p, 4p, 5p, 6p, and then the d's, 3d, 4d, 5d, 6d, and then finally the f's, which we don't really talk about much. We don't have to worry about them too much. So starting at 4 equals 4, we have 4f and then 5f here. And the way it goes is if you start from the top right-hand corner and go down to the left-hand corner, you're going to draw a line through each of these here. So we do 1s first, that's number 1. Then 2s second, that's number 2. Okay, line number 3 first goes through 2p, then 3s. Then we get 3p followed by 4s for line number 4. Then finally, moving on, after the 4s, we get 3d, 4p, 5s. Next up, 4d, 5p, 6s. Then finally, we get to the f's, right? So this is where we get 4f, 4d, 5d, 6p, 7s, and then wrap it up with 5f and 6. I'm sorry, that's 8. So that's how you can do it, even if you don't have this memorized up here. There's an even easier way to do it, which is using the periodic table. But since we haven't done enough of these electron configurations yet to discover that, we'll just look at it this way for now. Oops, there we go. Okay. So here we go. This is how we're going to write electron configurations. And I know you're probably ready for some practice now. The lower energy orbitals are always going to fill before the higher energy orbitals. And these orbitals can hold no more than 2 electrons each. When 2 electrons occupy the same orbital, they have to have opposing spins. That's the Pauli exclusion principle. When you have orbitals of identical energy available, all of those are first occupied singly by electrons that have parallel spins rather than pairing the electrons. That's the Hund's rule. Okay, so as we move on from carbon, we get to nitrogen, which is 7 electrons. That's 1s2, 2s2, 2p3. So Hund's rule tells us we're going to put those 3 electrons each singly into the 3p orbitals. Next up with oxygen, finally, we're at 2p4. So now we have to pair the first p orbital here. With fluorine, we have now 9 electrons. We have to pair the second. And then finally, neon with 10 electrons fills the 2p sublevel and gives us 3 filled 2p orbitals like that. Okay, so why don't you go ahead and give me the electron configurations? And, let's go ahead and do the orbital diagrams as well of A through, let's skip lead for now. I think lead is a little, hold on. We're going to skip lead. You didn't see that. You're not seeing that. Okay, great. Okay, don't pause the video on those answers. Okay, I want you to actually try this for yourself here. Give me the electron configurations for each of these following elements, and then we'll look at the answers here on the next slide. So go ahead, pause the video now, work on these, and then we'll walk it through in just a minute. So go ahead, pause. I'm going to take a sip of tea. When we're back, we'll give it a shot. Okay, all right, here, I think we're ready for it. Let's go ahead and start with oxygen. Oh, well, hopefully you got this one, right? Because we just had it on the previous slide. That's 8 total electrons, 2 in the 1s, 2 in the 2s, 4 in the 2p. Next up, aluminum. Well, how many electrons do you have in aluminum? You have 13 electrons in aluminum, right? Oh, yeah, I did it right. Okay. So the first 2 in the 1s, the second 2 in the 2s, then you have 6 in the 2p, then you move into the 3s, that's 3s2, and the last one into the 3p, so 3p1. Okay, next up we got iron. Now iron's a big one, right? There's a lot of electrons there. So we start out just the same as we were doing before. 1s2, 2s2, 2p6, 3s2. Now we fill up the 3p with 6 electrons. Then we have 2 more electrons into the 4s. And then finally 6 electrons fit in the 3d. Remember, those d sublevels can fit 10 total electrons. Okay, finally, the hard one here is tellurium, right? Other than lead, of course, which, as I mentioned, we're just not going to worry about. For tellurium, now we've got 2 in the 1s. So 1s2, 2s2, 2p6, then moving to 3, 3s2, 3p6, 4, 4s2, 3d10, 4p6. Next up, 5s2, 4d10, 5p4. Okay. And again, lead is really nasty because it involves F sublevels. We're not going to worry about that in this class. Okay. Now, something that you might notice as you do that, you might notice that, hey, I have to write the same sublevels all over again all the time. And isn't that kind of annoying? And sure enough, it is really annoying. So what we do is, as a way of showing that, the core electrons in an element aren't likely to react, as we've mentioned before, valence electrons, those are the outermost electrons. Those are the ones that tend to be involved in chemical reactions. We're really only interested in the valence electrons if we're interested in studying chemical reactions. So what we do, instead of having to write out 1s2, 2s2, 2p6 all the time, is we use what's called noble gas core notation. So when we have an electron configuration for any element beyond neon, the electron configuration of the previous noble gas is assumed, and it's abbreviated by writing it in brackets. So sodium is a really good example, right? Sodium is element number 11. So that's just one electron extra from neon. So sodium you could write as 1s2, 2s2, 2p6, 3s1. But these 10 electrons are just the same as neon. So what we do instead is we put the neon in brackets here, the noble gas, and then write the valence electron 3s1 as its as the only notation that we really have to write. Now, a couple notes. This only works for noble gases. So you can only use neon, argon, krypton, xenon, and I suppose radon, although we'll never make it that far. So neon, argon, krypton, and xenon. No other elements work this way. So don't try to use some random metal or something like that. So yeah, instead you're going to make sure to just use the noble gases to represent the core electrons. Okay, so this word valence electrons, just to make sure we define it here again, these are the electrons that are in the outermost principal shell, and that is the principal shell that has the highest principal quantum number, along with the d electrons that would go along with that, right? So for example, moving beyond argon, for example, you move into the 4s sublevel and then into the 3d sublevel. Those are also going to be considered valence electrons when you're in the transition metals. Now, those electrons are important because those are the ones that are involved in covalent bonding, like we mentioned, and the electrons that are not in the outermost shell are what we call core electrons. Okay, so looking at silicon, for example, silicon is element number 14. So it has, in group 4a, 4 valence electrons. And the way that we can see that in the orbital diagram or in the electron configuration is, well, the first 10 electrons are all the same as the configuration of neon. So that's 1s2, 2s2, 2p6. Those are the core electrons, the 1s and the 2s. The valence electrons are going to include those in energy level 3. So 3s2, 3p2. Again, that's 4 electrons, that's 4 valence electrons, just like we predict. Okay, now selenium, on the other hand, selenium is element number 34. So, okay, so this is kind of a rough example here, but remember, selenium has the core electrons of argon, right? Okay, yeah, so it's the core electrons of argon. Then you fill the 4s sublevel, then the 3d sublevel, and then finally the 4p sublevel. N equals 4 is the highest number here. So those are going to be our valence electrons. 3d10, once it's full, it's basically set as a core electron. So even though we write the core electron notation, including argon, once the 3d sublevel is full, those are also core electrons there too. Okay, so go ahead and write the condensed electron configurations for each of these. I think we're going to skip polonium, I believe. Yeah, so do not do polonium. We're going to skip that one for today. So skip polonium. And when you come back, we will take a look at the answer. So we're going to pause the video here, and we'll take a look at the condensed electron configurations when we come back. So pause. All right, oh, did I have these on the slide as well? There we go, okay. So for silicon, this should be easy. This is the one we just looked at. It's got the core electrons of neon, followed by 3s2, 3p2. Next up for calcium, what's the nearest noble gas neighbor to calcium? Well, calcium's number 20, and its nearest noble gas neighbor is argon. So it's argon, and then plus 2 extra electrons. Those both fit in the 4s sublevel, so 4s2. Next up, we have nickel. Nickel is in the transition metals there. So it fills argon first, then the 4s sublevel. Then we move into the 3d sublevel. And we have 1, 2, 3, 4, 5, 6, 7, 8 more electrons there. So 3d8. Finally, iodine, which is a real nasty one. So iodine is number 53, and its nearest noble gas, as far as like previous noble gas core electrons, is going to be krypton. Then moving on from krypton, we have to fit the next 17 electrons in. So the way to do that is we move first into the 5s sublevel, 5s2, then we fill the 4d sublevel, 4d10, and then finally we go 1, 2, 3, 4, 5 p electrons, so 5p5. And again, we're not going to worry about the f sublevel, so don't worry about that for polonium. Okay, now next up, write the orbital diagram and determine the number of valence and unpaired electrons for the following elements from sample exercise number 2. And basically what you're going to do now is you write the orbital diagram based on the what we just had on the previous slide. And then that's only going to be for the valence electrons. So only valence. So don't worry about doing it for the core electrons, just for the valence electrons. Once you have those valence electrons drawn in an orbital diagram, then you can count the total number of unpaired electrons, which is just, you don't really need to care about this too much, but that's what basically makes a compound magnetic or not, or an element magnetic or not. So let's go ahead, pause the video, work on those orbital diagrams for the valence electrons again for these from what we were just looking at, and then tell me the number of unpaired electrons that there are. So pause the video. Okay, and I think we're ready to go ahead and check this out. So I didn't put the answers on here. So let's go ahead. Let's go ahead and look at a previous one here, and we'll go ahead and do the answers here together. There we go. Okay. So for this one here, for silicon, the valence electrons, we have 4 total valence electrons, 2 in the 3s and 2 in the 3p. So when we draw the orbital diagram, we've got the 3s, oops, boy, and the 3p. It's a little messy. Okay, the 3s is full. It's got 2 electrons, so those are both paired. Okay, and we have 2 in the 3p, so that's 1 and 2, like that. So when we count it up, of course, that's just 2 unpaired electrons. Okay, next up, calcium. Calcium's pretty easy, right? This is nice. It just is 4s2, right? So that means you have a filled 4s subshell. So 0 unpaired electrons. Yeesh, 0. That's what I get for trying to do that. Okay, nickel. Now nickel is 4s2, 3d8. So we first draw the 4s sublevel, and it's got 2 electrons. Next up, we draw the d. So how many orbitals are in the d sublevel? 5 total orbitals, right? So let's draw that out. Okay, that's 1, 2, 3, 4, 5. Okay, great. And now we're going to fill it. Okay, man, this is going to be a really rough one here, but I'll do my best. So remember, we fill using Hund's rule. So we're going to do 1 first, pointing up in each of them. So that's 1, 2, 3, 4, 5. And then we're going to come back here and pair it. 6, 7, 8. Okay, so here then there's 2 unpaired electrons again. Okay, next up for iodine. Remember, we only need to do that valence electron, so we're not worried about the 4d. And anyway, it's full, right? So that means it's paired. So we have the 5s sublevel with 2 electrons, that's full. Then we have the 5p sublevel with 5 electrons. So again, filling it according to Hund's rule, we're going to go up, 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 and then we just have 2 left, down, down. So that's 1 unpaired electron. And then we didn't do polonium, so that should be good. Okay, so check that out for your answers there. We're going to go ahead and clear this and move on. 3, okay, great. Now, we did all of that, but I'm about to tell you that there's a huge shortcut that you can use because the periodic table itself is a really good map of electron configurations. As we're about to find out, the shape of the periodic table is based on these electron configurations. So the elements that are within a column all have the same number of valence electrons and also have similar outer electron configurations. So for example, the alkali elements in hydrogen all have 1 electron in an s sublevel. The alkaline earth metals all have 2 electrons in their s sublevel. Then we move over to, for example, the halogens, which all behave very similarly. They each have 7 total valence electrons, with 2 in the s sublevel and 5 in the p sublevel. Fluorine, for example, is 2s2, 2p5. Chlorine is 3s2, 3p5. And then finally, noble gases, including helium, these all have a full sublevel. So like 2s2, 2p6, those are all paired electrons, and those paired electrons are not reactive. So that explains why the noble gases are unreactive. Okay, so this is the overall pattern for, again, the periodic table. The first 2 columns, so that's these guys right here. Notice that sticks up. Well, the reason that it sticks up is because that's where you're filling the S sublevel of each energy level. And so that's what we call the S block. Then we have this big box over here that's about 6 blocks wide. That's what we call the P block, because in there we're filling the P sublevels. The transition metals in the middle, notice that that's 10 wide. That's 10 wide, and it's called because we're filling the D sublevels, so we call it the D block. And then finally down here, this is the F block down here. It's a little complicated. Sometimes it goes over to 15, but there's basically essentially 14 elements that are here. There's just debates over which one should be, you know, on numbers 57 and 89 on the periodic table. So yeah, so that's what we call the lanthanides and actinides. We're not going to really worry about that too much. Okay, so here's how it goes, right? So this is the pattern for the periodic table. 1s1, 1s2. Start back over. 2s1, 2s2, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Again, over here, we're filling the P block. We go back over to the S block. We're filling the next S sublevel, 3s1, 3s2. Then we move over to the P block. We're filling in the P sublevel, 3s2, 3p1, and then 3p2, 3p3, 3p4, 3p5, 3p6. We're done on this side. So we go back over. Now we're in S block, 4s1, 4s2. Notice that these, for the S and the P's, all match up with the number of period that's in. So in period 3, you're filling the 3s sublevel and then the 3p sublevel. Now it breaks down a little bit when you get to the D sublevels in the D block, because remember, the 4s comes first, then the 3d. So just keep in mind that it's n-1 for the D block. So you go 4s1, 4s2, then 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. Now, I mean, that's theoretical. As you can see, it actually varies a little bit, annoyingly, with chromium and copper for reasons that are beyond the scope of this course. So, but that's the idea. Now, once you fill the 3D block, now you're in the 4P block and you're ready to fill 4P1, 2, 3, 4, 5, and 6. Okay, so the valence electrons for any main group element is equal to the group number of its column, with the exception of helium, which has 2 valence electrons. Chlorine has 7 valence electrons because it's in group 7A. The row number in the periodic table is equal to the number of the highest principal shell. That's for the S and the P block especially. And remember that the D block has a different rule. That's for n-1. And yeah, the main group elements, those are the ones that are the 1A through 8A. So that's the S block over here, plus the P block, ignoring the transition and intertransition metals. Okay, so again, okay, yeah, oh, so now we bring up the transition metals here. The trends differ a little bit, where it's usually, the configuration is gonna be 4s2, 3dx, where x is the number of d electrons, with exceptions for chromium and copper. Basically, the reason for that is half-filled shell gets an energy bonus. And so you get a little bonus when you have a half-filled energy shell. For chromium, you have 2 half-filled shells. And then for copper, you have a half-filled and a full shell. So, but don't worry about that. I'm not expecting you to memorize that for this class. Okay. Yeah, now remember that the outer shell electron number doesn't change. So you'd have, for 4s2, 3dx, you'd have 2 electrons in your outer shell. So we're just going to say that it's 2 electrons in the outer shell. Okay, so now how do you write a electron configuration based on the periodic table? Because this is actually how I do it. I don't try to remember the order of things. I can tell it all from the periodic table itself. So knowing that we start from 1s, for example, we know that the first period is just going to be 1s1, 1s2. Okay, and now to make it even easier, we know that we have the core configuration. So, okay, so if we're going to write the electron configuration based on the periodic table, pick a random element like phosphorus. So start first from the core electron configuration. So for phosphorus, the previous noble gas was neon, number 10. So that's going to be our core electron. So let's go ahead and write that down. Oops. Okay. Next up, where do we go after neon? Well, after neon, we go to period 3, sodium. And sodium's in the S block, so we're going to fill the 3s sublevel next. So we go sodium, magnesium. We're not to phosphorus yet. So that means we must have filled the 3s sublevel, 3s2. And remember, it should be superscripted. I just can't do that on the Zoom telelink here. And then count over, once we're in now at aluminum, okay, we're at aluminum, and now we got 1, 2, 3 more electrons. So those 3 electrons all fit in the P sublevel, the 3p sublevel. So it goes 3p3, like that. And that's all you have to do. You find the core electron configuration, then move across in the periodic table, identify what orbital is being filled next, and then you're ready to just fill out the valence electrons. So this is a way to make it just easier. So just to kind of like state it out in word form, you know, the inner electron configuration is the electron configuration of the noble gas that precedes that element. And again, we put the symbol for the noble gas in brackets. Then the outer electrons are going to be determined from the position of the element within a particular block. And you just trace the elements that go in between and put the electrons in the appropriate orbitals. Yeah. Okay. Okay, so now why do we explain all of this with electron configurations and orbital diagrams? Well, as it turns out, understanding the electron configuration of an element is really powerful to predict its chemical properties. So for example, let's look at sodium and fluorine. Sodium tends to form sodium ions, and fluorine tends to form fluoride ions, sodium ions being 1+, fluoride being 1-. Now, what else do we know? Some elements are metals and others are nonmetals. And why is it that noble gases are chemically inert while the alkali metals are very reactive? Well, as it turns out, the chemical properties that we talked about are determined by the number of valence electrons that they contain. And those properties vary in a periodic fashion because the valence electrons varies periodically as well. Starting with the noble gases. So noble gases, when we have 8 electrons in a filled S and P sublevels here, these electrons are very stable. So they're very unlikely to react. In other words, you have to really put in a lot of energy to get an electron out. And that just doesn't happen much in nature. So elements that have electron configurations that are similar to noble gases are the most are the most stable. If it's close, if it's almost a noble gas, like fluorine, for example, that element's going to be very reactive to get to the noble gas configuration, where again, its electrons are all stable. Alkali metals are a good example of this as well. These are among the most reactive of metals because they only have one valence electron, meaning that if they give up their one single valence electron, they're able to achieve a noble gas configuration. And that's why all of these metals form a +1 cation. Alkaline earth metals, similarly, only have to give up 2 electrons. So to give up 2 electrons, it takes a little more energy than giving up 1 electron, but it's still very doable. And that's why you often see magnesium. You rarely see magnesium as a pure metal, and much more often see it as a ion. Same thing with calcium. In all of the reactions that they do, they tend to lose these 2 valence electrons, again, to achieve a noble gas configuration. Now, how about the halogens? Well, the halogens all form -1 ions. Why is that? Well, if they get one more electron, fluorine, chlorine, bromine, iodine, etc., then their electrons are the same as the nearest noble gas. So it's fluorine, when it gains an electron, becomes 2s2, 2p6. So it achieves the noble gas configuration of neon, the electron configuration of neon. So that's, again, a stable electron configuration. So because it's so close to being stable, that means it wants that electron very much. So remember, this is from our predictable ion chart. Remember that metals in group 1 and 2, 1a and 2a, all form +1 and then +2 respectively. Group 3a forms +3. Group 7a forms -1. Group 6a forms -2. And group 5a forms -3. Again, each of these ions form because when they either give up those electrons or gain those electrons, they are able to achieve a noble gas electron configuration. Okay, so that explains why ions form. Next up, why don't we talk about the size of an ion, or the size of an atom, excuse me. And as it turns out, the size of an atom actually has 2 separate trends. We have a trend left to right across a period, and then we have a trend top to bottom. Okay, so now we'll start with the most difficult one to understand. As you go left to right across a period on the periodic table, the atomic size actually decreases. Now this goes against what you might think because, oh, you're going left to right, you're adding more protons to the nucleus, you're adding more electrons to the electron orbitals. So surely the size must increase, right? But that's not the case. Remember, the atomic size of an atom is the distance between the nucleus and the outermost electrons. So when we add in protons to the nucleus, what we're doing is we're increasing the charge of the nucleus. But when we add electrons to the orbital, we're keeping it at roughly the same distance. So if you keep a stronger positive charge, that stronger positive charge nucleus is going to pull on those electrons more and actually going to make the atom constrict as you go left to right across a period, because it has a stronger effect, stronger pulling effect on those electrons. So again, that's why we see as we increase the number of protons in the nucleus, we decrease the atomic size as we go left to right across a period. Now, that doesn't take into account when we go down a group. So as we go down a group on the periodic table, the atomic size increases. And the reason this makes sense is, remember, the 2s sublevel is bigger than the 1s sublevel, and the 3s sublevel is bigger than the 2s sublevel, and the 4s sublevel is bigger than the 3s sublevel, et cetera, et cetera, et cetera. So as we increase the electrons that we're putting into that principal quantum number, the orbital principal quantum number, the size of the atom is going to increase. And so that's why we see atomic size increasing as we go down a group. So this is kind of a rough demonstration of what that looks like. Again, left to right, going lithium to fluorine, it gets smaller, but top to bottom, lithium to cesium, we just get bigger. The other way you can remember this is that fluorine or neon, depending on which one you're looking at here, is the smallest element or the smallest atom. You can also say helium, I suppose, although hydrogen and helium are like kind of hard. They're really tiny, so it doesn't really make sense. I always try to think of neon as the smallest element here, and that basically tells you both trends, right? So it has to decrease left to right, and it has to decrease going up. Okay, so given that information, go ahead, pause the video here, and try to choose the larger atom from each pair between calcium and beryllium, sulfur and aluminum, chlorine and potassium, and beryllium and nitrogen. Pause the video, and when you come back, we'll take a look at the answers. So pause. Okay, let's go ahead and take a look. So look at calcium and beryllium. Well, calcium is below beryllium on the periodic table, right? And as we go down a group, we know that atomic size increases. So calcium's the bigger atom. Sulfur versus aluminum. Okay, sulfur and aluminum are in the same period, and sulfur is to the right of aluminum on the periodic table. As we go left to right, the size decreases. Therefore, aluminum must be bigger than sulfur. So aluminum. Next up, chlorine and potassium. So chlorine and potassium. Chlorine is in group 7A. Potassium is in period 4. So we have a couple countervailing trends, but actually it works out either way. Remember, the left side is bigger than the right side, and then also the bottom is bigger than the top. So because potassium is both below chlorine in the periodic table and to the left of it, we know that potassium has to be bigger. And then finally, beryllium versus nitrogen. This is easy because they're in the same period. As you go left to right, size decreases, so beryllium must be bigger. Okay, the next periodic property that we need to know, ionization energy. Ionization energy will increase as you move to the right across a period, and it decreases as you move down a column in the periodic table. So decreases going down, increases going left to right. Now, what is ionization energy? I should have probably put this here. Ionization energy is basically you take an element, we'll call it E, and what you do is you add in energy. This is the ionization energy. So, okay. And what happens is you're trying to strip away an electron. In other words, ionize. So what you get is you get E, the E ion with a positive charge, plus you removed an electron like that. So this is the ionization energy here. It's basically how much energy is required to remove an electron from an atom. And as it turns out, as you go left to right across a period, it gets harder to do that. Here's my annotation. Let's move this up and this up. So as you go left to right across a period, it gets harder to do that. Now this makes sense because remember, as we move left to right across a period, the electrons are getting closer to the nucleus. And the closer that the electron is to the positive charge of the nucleus, the harder it is going to be to pull those electrons away. So it's easier when you have bigger atoms. Those are on the left. Same thing as we go down. Now, again, as we go down a group, the atoms get bigger and bigger. So what that means is it's going to be easier to pull away an electron from the outside because they're farther away from the positively charged nucleus. So this ionization energy decreases going down a group, and it increases going across a group. Okay, so given that information, go ahead, choose the element with the highest ionization energy from each pair. Don't worry about the first ionization energy. We just are worried about ionization energy total. So bromine versus bismuth. Is that right? Did I give you the right one here? I'm just trying to make sure I did not mess it up here. Okay, bromine versus bismuth, silicon versus chlorine, and then calcium versus gallium. So go ahead, give it a shot on these. Try to pick the one that has the highest first ionization. Yeah, pause the video and we'll be back in a second with the answer. Okay, so first up, for bromine versus bismuth, bromine is to the right of bismuth, and it's also above bismuth, meaning that it's going to have a higher ionization energy with both trends. So we know that bromine has the higher first ionization energy. Silicon versus chlorine, those are both in the same period. Chlorine being to the right of silicon means that chlorine is going to have a higher ionization energy. So we pick chlorine for that one. Calcium versus gallium, those are both in the same period. So calcium is to the left of gallium, so that one should be easier to ionize. So actually, whoops, this should be the higher first ionization energy. Oops, I have that exactly wrong. It should be, let's just move this over, should be gallium for this one here, the higher ionization energy. There we go, cool. Okay, so that's gallium. All right, finally, we have our last periodic property, which is metallic properties. Now, we mentioned this before when we talked about metals versus nonmetals. Notice how on the left side of the periodic table, that's where metals are. And on the right side, that's where nonmetals are. We know that metals tend to lose electrons when they react, and nonmetals tend to gain electrons when they react. So metallic character is a periodic trend because it decreases as we go left to right across a period, and it increases as we go top to bottom down a group. We can see this in, for example, the second period. We start with the metals lithium and beryllium on the left, and we end up in the nonmetals, nitrogen, oxygen, and fluorine on the right. So clearly metallic character is decreasing as we go to the right. Then look at, for example, group 5A, group 4A, for example. So group 4A starts with carbon at the top, carbon, classic nonmetal. And then at the bottom, we get to tin and lead, which of course are metals. So clearly, metallic character is increasing as we go down a group. So that brings us to this trend here again. Metallic character increases going down a group, and metallic character decreases going left to right across the periodic table. Oh, oops. Well, okay. So good enough. I guess my trick question didn't trick you here because it just says can't determine already. Go ahead and choose the more metallic element from each pair. First with strontium and antimony, then we have arsenic and bismuth, and then finally chlorine and oxygen we can't determine. So go ahead, take a moment, pause the video, and when we come back, we'll take a look at this. Okay, so we've got strontium and antimony. Well, strontium is a metal, and antimony is a metalloid, so strontium is definitely more metal in character. And then finally, we have arsenic versus bismuth. Bismuth is a metal and arsenic is a metalloid. So again, bismuth you would expect to be more metallic in character, and that fits our trends. Okay, well, that covers us for chapter 9. We'll be moving on into chapter 10, and we'll talk about how these electron structures actually form covalent compounds. But until then, make sure you work on the homework for chapter 9, and I will see you soon. Bye-bye.